Hello again, this is Professor Roman. Let's continue the lecture series, Transition to Advanced Mathematics. To conclude our discussion of logic, I wanted to talk about a couple of things that won't be central to what we're doing in the future, but I think are interesting, especially if you enjoy logic. One is the issue of what are called normal forms. We've seen that every well-formed formula has a truth table. And that truth table describes the logical structure of the formula. It tells us when it's true and when it's false. But what about the converse? Suppose we are given a logical structure as represented by a truth table with, say, 2 to the n rows. Is there a well-formed formula with n variables whose truth table is that given table? This is the converse. I should probably mention that you will encounter lots of conditional statements as you study mathematics. And it's a good idea whenever you do encounter a conditional statement, perhaps it's one that you found yourself, not that you read in a book, you should ask yourself, what about the converse? Does the converse hold? Many times it won't, but many times it will, and so you can upgrade your conditional statement into a biconditional statement, which is much stronger, of course. So in short, always give some thought to the converse of any conditional statement you encounter. And that's what we're doing here. This is the sort of thing a mathematician will do. He or she will find a conditional statement. Every well-formed formulas have truth tables, and ask about the converse. Do truth tables always have well-formed formulas associated with them? So let's look at an example. Here's a truth table, 8 rows, and I've indicated where the final value is true with arrows, 4 of them. In order to find a well-formed formula that has this truth table, we can proceed as follows. First, we locate the rows that end in t, which I just did. For each of these rows, we create a conjunction that looks like this: E1 and E2 and E3. 3 variables, 3 terms. And E1 is x if the first column has a t in it. Otherwise, it's not x. It's the negation of x if the first column, if the x value, in other words, is false. Okay? And the same for the other rows. So this is what we end up with. The first row ends in, let's see if I could squeeze all this in together at one time. Okay, the first row is TTT and it ends in a T. So I have X and Y and Z. The next row with it that ends in true, it's TFT, so I have X and not Y, because Y is false, and Z. The third row that ends in T is FTT, so I have not X, Y, Z. And the final row that ends in T is all falses, so I have not X and not Y and not Z. Now, the individual well-formed formulas that I've constructed, these little conjunctions, have the property that they are true if and only if the variables have the truth values given in the corresponding row. So for example, for row 1, this is the well-formed formula. And this is true if and only if all three variables are true. In other words, if and only if the variables have the values from row 1. So the truth table of this by itself would have a t in the first row and all falses from then on. Similarly, this well-formed formula, which comes from row 3, is true if and only if the truth values of the variables x, y, and z are the ones in row 3. True, false, true. It follows then that the disjunction of these two formulas will have, when you look at the truth table, will have a t will be true if and only if the variables have the corresponding truth values from either row 1 or row 3. And more generally, if we take the disjunction of all 4 of these statements, we will get a well-formed formula that is true precisely in those 4 rows of the table that have value true. In other words, this well-formed formula has this truth table. So it's a simple algorithm for constructing a well-formed formula that has a given truth table. A formula that has this form, that is the disjunction of special types of conjunctions, is said to be in disjunctive normal form. There's a corresponding conjunctive normal form where each of the individual terms in parentheses would be disjunctions, and then you would take the conjunction. In other words, you reverse the ands and the ors. It shouldn't be too difficult to see that this algorithm I just gave you will compute a well-formed formula that matches any truth table except one that has no t's in its final column. If it's all f's in the final column, then it's a contradiction. It's always false. But then a well-formed formula that looks like this is also a contradiction. It's always false. So we can always handle that case of a truth table that's all false separately. Okay. So the disjunctive normal form together with this one extra form will cover all cases, all truth tables. So we can find a well-formed formula that has any given logical structure that we want. Another thing I wanted to talk about is the following. Do we really need 5 basic connectives in order to realize any given logical structure? Or put another way, any truth table? Expressed in terms of well-formed formulas, is there a proper subset of the 5 basic connectives with the property that given any well-formed formula, there is another well-formed formula, omega prime, that uses only the connectives in the subset, but that's logically equivalent to the original well-formed formula? Well, the answer is yes, and it's not that hard to see. If we toss away the biconditional and take only the 4 basic connectives listed here, we can still form any logical structure, because the biconditional S if and only if T is logically equivalent to S implies T and T implies S. So in any formula that involves the biconditional, we can replace that biconditional by admittedly more complicated formula that only uses conditional statements, doesn't use the biconditional. So for example, if you look at this well-formed formula, it's logically equivalent to this one, where I've replaced not Q if and only if R by not Q implies R and R implies not Q. Okay. So at the expense of having longer and formulas that are more difficult to read, we don't ever need to use a biconditional. Similarly, this conditional, as we've seen before, is logically equivalent to this well-formed formula, so we don't even need the conditional. We can toss both the biconditional and the conditional and come down to three connectives that would suffice to construct all possible logical structures. In other words, you get all the well-formed formulas we need from just these three connectives. In fact, De Morgan's laws tell us that P and Q is logically equivalent to not P and Q, because negation's an involution, and then slipping one of the negations inside, using De Morgan's laws, not quantity, not P, and not Q, so we can dispense with disjunction, and just negation and conjunction are enough to express all logical structures. Similarly, we could do without conjunction if we keep negation and disjunction. So these two sets, either one, suffice to express all well-formed formulas, or at least logically equivalent to all well-formed formulas. And this calls for a definition. A set C of connectives is adequate if any well-formed formula, a spelling error there, that involves the five basic connectives is logically equivalent to a well-formed formula involving only the connectives in the set C. So we have here we have these two adequate sets, and this is also adequate, negation and implication, and I'm going to leave that for you to justify. So these three sets are adequate, and they only involve two connectives. So in a sense, they're much more efficient than using all five, but in the other sense, they make well-formed formulas almost impossible to read. So a computer wouldn't care, but we would care. Well, this brings up another question. All of these sets of adequate sets involve negation. Is that required? Is negation required? Another interesting question, could there be a single connective of some type that is adequate to express all well-formed formulas up to logical equivalence? It's not going to be one of the five basic connectives, but those aren't the only connectives. You know, a connective involving two variables is defined by a truth table with 4 rows. There are 16 possible truth tables like this. So there are 16 connectives, some of which are of no use. But we've only talked about 4 basic connectives. The negation is just a 2-row table, so it's a little different. Well, the answer is yes, there are, in fact, 2 connectives that are adequate all by themselves, and they don't and neither one is negation, so that answers the previous question as well. One is called the Sheffer stroke. It's denoted in various ways, but common ways are with an arrow pointing up or just a vertical bar. And this is the truth table. True, true, false, and all the other rows are true. This connective was named after Henry M. Sheffer, who introduced it in a paper written in 1913. Okay. 3 years after I was born. Anyway, the truth table for the Sheffer stroke is, if you will notice, the same as the truth table for this well-formed formula, not P and Q. And for that reason, the Sheffer stroke is also referred to by the acronym NAND, N-A-N-D, not AND. Okay. This is not AND, in fact. Now, since negation can be expressed with the Sheffer stroke, not P, logically equivalent to not P and P, which is logically equivalent to P stroke P, and, excuse me, disjunction can also be written in terms of the Sheffer stroke. It's getting a little nasty here, but it can be done. Then the adequacy of the set, negation and disjunction, implies that the Sheffer stroke all by itself is adequate. So we can use the Sheffer stroke, and only the Sheffer stroke, to get all possible logical structures. But we pay a heavy price because, these are, you can see that they're beginning to get complicated. And P stroke P, I guess you'd read this quantity P stroke P, stroke quantity Q stroke Q. It's getting very awkward. The other connective that's adequate all by itself is called the Pierce arrow. And it's not the car company, which you're probably too young to remember, but there was a car company called Pierce Arrow. There was a car called a Pierce Arrow. This is denoted by a downward arrow, and it's logically equivalent to not P or Q. So the acronym is NOR, which is also a common word, NOR. Here's the truth table, all falses except the last row, which is true. And I'm going to leave that for you to show that this is adequate all by itself, the Pierce arrow. What are the consequences of, well, mostly this theorem here, that these are adequate sets? What are the consequences of that for non-mathematicians or for those who do not specialize in logic? Well, the theorem tells us that any English statement can be rephrased to get a logically equivalent statement that doesn't use the words implies or if then or if and only if. So for example, if it is raining, then I will carry an umbrella can be rephrased as it is not raining or I will carry an umbrella. Now, strictly speaking, in terms of English, there's quite a different feel between these two statements. But we're not studying English, we're studying logic. And these are logically equivalent, so we know that they have the same logical structure. They're true at the same time, they're false at the same time. It might seem a little closer to the conditional to say it is not raining or else I will carry an umbrella, but this statement, I will pass this class if and only if, whenever a test is coming, I go to the library to study, has this symbolic form. It's a biconditional and a conditional. So if we assign variables in the usual way, the biconditional first gets split into a conjunction of conditionals, and each of the conditionals can be removed, as we've seen, and we get something that looks like this. It's getting a little nasty. Here it is, cleaned up just a hair. Okay. And so we can phrase this in English as follows. I will not pass this class, or no test is coming, or I will go to the library to study, and a test is coming, and I will not go to the library, or I will pass this class. So I guess that's pretty obviously the same as the original statement. If I will pass this class if and only if, whenever a test is coming, I go to the library to study. So you can see that from the point of view of English, of any language, reducing the set of 5 basic connectives to an adequate set is of no value. Just serves to complicate English dramatically. This is unreadable. You can't make any sense out of this, really. But in any case, it is of some theoretical value to know that there are adequate sets of connectives that involve either one or two connectives. If you're building logic circuits, I'm not going to discuss that in this class because we do need to move on. But you would build logic circuits with AND gates, OR gates, and NOT gates, also called inverters. So you can build logical circuits that will model any logical structure, but you have to use 3 types of what are referred to as gates, and that involves some expense. If you only can construct one type of gate, you could construct the Sheffer stroke gate, and you could build all circuits using just the Sheffer stroke gate. Now the penalty you pay is you're going to have a lot more gates, but the advantage is you only have to build one type of gate. And I'm not going to pass judgment on whether that makes sense or not, but it is an option that's available. So this is one reason why knowing that there are small adequate sets of connectives might be of some practical value. I'm not an engineer, so I can't tell you for sure whether it is of practical value in any particular situation.